say what are the values of, what are the expressions for VH and VL, the two voltage drops. So VH is equal to minus B over NEC IX, and there's a VL. Okay, now, sorry, I confuse you with notation. Let me call this then 2W, so that, I mean, script W, because we had used another W here, the width of the sample. So VL is in fact equal to L over W sigma naught times IX. So it's the same IX that you are driving. The way you are driving is because you have a source of electrons here and a certain value of chemical potential in the sense of thermodynamics. Chemical potential is the Gibbs energy per particle that I create. So it's one chemical potential here, one chemical potential there, and so there's a net change in chemical potential, so I have a drive. I have a source of electrons moving in this direction. It is like, again, you go back to more than 200 years ago when Fourier considered heat propagation because he was interested in conductivity. Actually, he wrote down the first diffusion equation. So you have a heat source on the left-hand side and a cold source on the right-hand side. There's a temperature gradient, and therefore you have a heat flow. Here you have you don't have a temperature is a problem, still a zero temperature problem that you can consider for the time being, but basically you have two different chemical potentials, okay, not heat potentials. And so, but you measure, with the same measured IX, you get two voltages, and it's therefore, this is the, this is what is called the Hall voltage, because if the magnetic field B was not there, then this voltage will not be measured. This will not be there in the system. So we get a Hall voltage. And so, now therefore, you now can consider what is called the off-diagonal term of a resistance, RYX, coming from, you see, how do I calculate resistance? From Ohm's law is simply voltage divided by current. But you see, this voltage actually is in a different direction than the current. That's why it's a new voltage depending on the magnetic field. And that has simply the value of B over NEC. So in the old solid-state physics books, you'll say the measurement of the Hall resistance gave you a handle on the number density, okay, of electrons. So carrier density is something that you calculate in semiconductors and other areas by simply making the Hall resistance. Now, it's an interesting property that, you see, this quantity is actually, so this is minus B over Ns, and the longitudinal component is the usual resistance that you have, which actually is here. So RXX is simply your Drude inverse, Drude conductivity inverse. Now it turns out, and that's where the dimension becomes, so the fact that this is independent of the magnetic field is because I have not considered magnetoresistance in the simple Drude theory. If there is magnetic scattering, then this resistance will also depend on the magnetic field. All right? Now, it turns out for quantum Hall effect, for 2D, the relevant quantities are resistances and not resistivities. So why, let me just give you, you remember your high school thing, that from resistance you define what is called resistivity. Let me see if I have some notes on this. Well, actually, okay, I remember. You all remember that you write resistance as resistivity times the length over the area. So if you think of a wire, cylindrical wire of a certain cross section, A, L is in this direction. So you say that electrons flow in this direction, normal to the cross section, and so this is resistivity. This is a three-dimensional concept. When you go to two-dimension, then you see there's no area anymore, right? And so it turns out that in 2D, resistance and resistivity are the same. Okay, so 2D is a special dimension where resistance and resistivity are the same. The same as resistivity. So these are the new concepts that come in when you go to low dimensional system. And so in quantum Hall effect, what you measure is actually resistance, which is like resistivity in 2D. And you in fact also measure what's called conductance and not conductivity. And conductance is normally introduced as an inverse of the resistivity, right? So anyway, so that's just the dimensional dependence that is forced onto you in making what you measure in the experiment. So yesterday we stopped here, and then now you combine this picture with what we discussed also yesterday or 2 days ago, is that what happens when you put electrons in a magnetic field and the effect of Landau levels. So you had a picture like this for zero magnetic field, and you put a magnetic field now, B not equal to 0. You have coalescing of these states into the so-called Landau levels. So J equal to 0, J equal to 1, J equal to 2. Each Landau level is highly degenerate. So the degeneracy is given as eta. And if you recall, eta depends on the magnetic field, depends on the charge, of course, and depends also on the area of the sheet divided by hc. So hc over E defines what is also called the flux quantum that appeared when we discussed the bomb effect. But very importantly, you find that the degeneracy is proportional to the strength of the magnetic field, and degeneracy also depends on the area. So now you can control the degeneracy by controlling the magnetic field in the laboratory. If you have a very large magnetic field, then you have a large degeneracy. Large degeneracy means that you have that many more states available to the electron. And so you'll see that your filling factors depend on the degeneracy, because if you have very large degeneracy, in particular if eta is greater than the total number of electrons, then you can accommodate all the electrons only the lowest Landau level. So we found out this interplay between capital N, the total number of electrons, and eta, okay, lets you have filled and unfilled Landau levels, right? So that's an experimentally manipulatable parameter, manipulatable control field in the laboratory. So by changing the magnetic field, you keep on changing the filling, right? And this is something that we discussed yesterday. They gave rise to the step behavior of the susceptibility, and as Mitra pointed out, that susceptibility step behavior is related to some behavior of oscillating magnetization, it's called the de Haas-Panalf and Shubnikov oscillations. And it's the same kind of phenomenon, because you have filled and unfilled Landau levels, gives rise to the integer quantum Hall effect. So in order to understand integer quantum Hall effect, you simply have to understand the Landau picture, put that in the context of the Drude model, and outcome is the quantum Hall effect picture. And it was measured by von Klitzing. as early as 1980. Got the Nobel Prize, I think, in 1984 itself. So von Klitzing, Max Planck lab in Stuttgart, right? Where is it? Stuttgart?
Yeah, Stuttgart. Just one. You finish?
Tell me.
So this was basically the classical picture. Then the full modern picture is using a Kubo formula right on the Kubo formula.
Yeah, but you don't need all that. You
Then you
simply
get the Chern number, the integer invariant.
yeah, but so that those are also there in terms of, I mean, for instance, when you just see the Landau picture and you put that in, you get all those things. Yeah.
Yeah, I'm just saying that for completeness.
Yes. Yes. Right. So I think my colleagues here know more about this subject, but I wanted to point out what I understood is that von Klitzing actually, what system did he use? I have it written down. So he used two different, actually, first he used probably silicon MOSFET or something, that's what I'm trying to see. Yeah. So the 1980 experiments of von Klitzing used silicon MOSFET. FET is field effect transistor. Have you seen this, the physics students? Yes. Okay. What is the expansion of MOS?
Metal oxide.
Metal
Semiconductor.
oxide semiconductor field effect transistor, MOSFET. And he could control, of course, the density electrostatically by a gate. And a rather high magnetic field was applied so that small values of the integer filling J can be achieved. Right? Because if you put in stronger and stronger magnetic field, most of the electrons will be shoved into the lower Landau levels. Later results, in 1982, just 2 years results on better quality heterostructures, and that's gallium arsenide as Dr. said, so it shows the effect more strikingly. Okay? So, in order to understand quantum Hall effect, you have to have a picture of what happens to the Landau levels. You have to have a picture of transport, but as was pointed out already, in the back of your mind, this is quantum transport, okay? And you also must know what is the effect due to disorder, localization, etc. Okay, and and then of course comes electron-electron interaction effects, strong correlation effects, etc., which will take you to the fractional quantum Hall effect regime. So very exciting things that happen. But it's a combination of all kinds of pictures. You have the Brownian motion picture of diffusion, you have the Landau diamagnetism problem combined with the Drude idea. That's the physics of quantum Hall effect. So physics is a two-dimensional physics. That's why graphene is a good test case to look at those things. Graphene has very well satisfies the time binding model, and that's why we spend so much time on the time binding model. And so now you have a concrete, coherent picture evolving why we put so much of focus on the 2D time binding situation. And I think at this stage, maybe we'll take a lunch break and we'll come back and finish off the series. Yeah? Any questions? these things took a long time to discover. That's the point I'm making. And unless you went down to those temperatures, those magnetic fields, you would not see such effects. Pressure is another attribute, and so how high you can go up to, and pressure, temperature, etc. So one of the things that is very interesting that happens is, so we did this whole bar. We again went back to the tight binding Anderson model. Where you had H as summation L, site energy minus hopping ELM LM plus ELM star ML, that is the Hermitian adjoint term. Okay. And we raised the issue, what would happen at epsilon L as disorder. Disorder characterized by an energy parameter which is on the width of the distribution of the disorder. Call it W, and so if T is a constant, then you have another parameter, define it as P over W. So high disorder would imply alpha is much smaller compared to 1, and low disorder would imply that alpha is much larger than 1. Okay, so if alpha is much larger than 1, it means that though there is disorder, your hopping term would prevail, and so I'll have conduction. So this is like metallic state. Low disorder means you have a metallic state, and you have an insulating states, because what will happen is that when the disorder is very large, it overwhelms the tunneling phenomenon, and so the electrons don't leak out to the sides, they get localized, and this localization would mean that I'm not able to see propagating electrons, so it's like insulating state. Okay? There's a very interesting example of this even in the double well problem, where the disorder is not due to a static disorder or a quenched disorder like this, but disorder in the sense of time. But remember what we said is that if I had a double well potential like this, and this we discussed in the first stage cell, that suppose you have a particle. So I have two wells in a lattice, which can be realized experimentally. And at time t equal to 0, I have prepared a wave packet which is localized in this well. And then if I let it go, if nothing happens, then of course this thing will keep tunneling back and forth. It's like a quantum clock. That's a very quantum coherent phenomenon. But there are two ways in which you can introduce decoherence. One is to increase the temperature. If you increase the temperature, then the de Broglie wavelength becomes fuzzy. That's the one source of decoherence. The other is that when you couple the system